Okay, so I've actually passed the tests. Okay, so a little context. We're doing 15445 CMU. Let's zoom in to 100%. There you go. Okay, so we're doing 15445 CMU B plus 3 indexes. Now, I don't. We're not. I'm not. I don't think I'm gonna need the code in order to show what's gonna happen here. I guess we're just gonna talk about what B plus 3 indexes are, essentially. Um, I also have some notes from today, and I also managed to implement delete today, which took me quite a long time. I do have to admit to that. Oh, there you go. Well, um, first things first, they're actually called differently in the course, which is quite interesting. I don't have cigarettes anymore, which is also quite bad, but I'll try to keep my smoking to a minimum. But I do love smoking. I'm one of those smokers that really loves smoking. Anyways, I'm trying to like organize myself here, but it's pretty hard because I don't have that much space. There you go. So, anyways, so what we're actually gonna talk about is billing trees. So what billing trees are, again, well, first of all, our memory model, so what I've actually done is implemented one of those billing trees. Okay, so wait 1 second. First of all, what billing trees are, they're sort of just ways of organizing um, a linked list. Well, let me, I guess, start by drawing this out. Okay, you should remember important thing. We have two constants. We have internal page max size. We're gonna pretend it's 3 during this talk, and then we have leaf page max size. Let's also pretend that this one is 3, I guess. Okay, so from these, our system will also derive. So we're gonna have two sort of objects that you can reason about. We're gonna have internal pages, right, which have this attribute over here, and then our system will sort of, okay, I'll actually have to look at this. This is what an internal page looks like, right? Yeah, we could actually use this. Well, let me, oh my god, my thing fell down. Anyways. Okay, so we're actually gonna start from this tree over here, and we're gonna reason from it. Right, so if you look at this, this is what, why can I paste this? Okay, we're having technical problems. There you go. This is what an internal page sort of looks like, right? You can see it has a max size, a min size. Now that min size is actually derived as right, it's the max size plus 1 divided by 2, which, well, it's just the seal of max size divided that by 2. So this in turn will guarantee, so we always know that, so these constants can actually be anything, right? But we always have sort of the guarantee that the internal page max size is bigger than or equal to 3, which then guarantees that the min size is bigger than or equal to 2. And we also have the guarantee that the leaf page max size is bigger than or equal to 2, which means that the min size is bigger than or equal to 1. Now for a particular leaf, like say this leaf over here, you can actually see that the min size is calculated as the max size, and then you're gonna have to just divide that by 2, which is just the floor, right? So you know that this guarantee over here holds, and the reason for why we do round up or round down is due to how we need to handle deletes in certain cases, which is, to say the least, a non-trivial activity. Well, anyways, you can sort of see that the overall scope of this. Now let's actually draw one out, right? Let's draw b plus tree out. Right, so drawing one out. Right, you can sort of see that the usual. Okay, I have one here, I think, on my thing. Okay, so we're gonna try to keep this, but I'm actually gonna keep, so you have to keep those in mind, right? We're always gonna be using those over here. Well, yeah, anyways, so the way we're gonna do it is we're gonna have something like x20. So one thing you should also note is that the first sort of element in an internal page, so you can see that this over here is an internal page, right? You can sort of just deduce that if it's an internal page, right? If it has the x here, if it has this x over here, that means it's an internal page. Anyways, we're gonna refer to pages. So pages are, for simplicity, nodes of the actual tree. Now, why do we call them pages? That is because this memory over here is actually backed by disk. So we have a component of the database management system that actually goes ahead and it goes to the disk, and what it does is it sort of, you ask it for a certain page ID. For example, you can see here that the page is 7, right? So if I were to draw it explicitly like this, the page is 7. And then the buffer pool manager, that's what this component is called. It actually goes to disk and it pulls out this page which has the unique identifier, in this case 7, and this page in this particular case is the root of the tree, right? So every single node is one page, and then one page is stored on the disk. When we want that disk to come into volatile memory, what we do is we ask the buffer pool manager to just hand us one of the pages, right? So why do we do that? We do that because essentially we want to have complete control over our own memory. We don't want to. So we want our memory to be backed by disk, but we don't want to use the OS primitives like mmap with like there's some flags that you can do with mmap, for example, on a Unix system that will synchronize those. But doing that is sort of stupid because the buffer pool manager actually allows you to have different replacement policies for when you run out of memory, and you want to be able to control that because essentially the way your memory is accessed, it depends on different things. And if you have like fine-grained control, you could modify it and like make an algorithm that's more optimized to reduce, for example, load stores from non-volatile storage, right, which is much slower. But that's like something we won't worry about now. So the mental model is this is in memory. It also is backed by disk, so pages are backed by disks. When they're in memory, they're also called frames. Anyways, a page, you can think of it as a node. Matter of fact, if you want to simplify your mental model, just think of everything as a node. Anyways, okay, so say, so this branch, what this means here, right? So the way you interpret this is this over here, this x means this is everything less than 20, and then here you have everything bigger than or equal to 20, right? So here's an exercise. Here's an exercise for you. Let's say you had something like page 1 with sort of 20, and then you had 30 here, right? Right, so it's clear that this is gonna mean nodes less than 20. This is gonna mean nodes that are bigger than or equal to 20 and less than 30, right? So they're in that interval. And then this is gonna mean nodes that are bigger than or equal to 30. And of course, this is an internal page, and this can actually go to another internal page. So there you go. Here's another internal page for you. I'm actually gonna be drawing, say, page IDs just to sort of have that mental model of, okay, these nodes are actually backed by pages. And if you want to know, look, we even have something like bus-stop page size, right, which is defined, God only knows where. There you go. It's equal to 8192. Right, so we can actually copy this. Right, so we have pages. Believe me, I've also implemented the other the other component, which is the buffer pool manager. Anyways, so this is the size of a page. Anyways, let's continue our journey over here, right? So that's bigger than or equal to 20, so can have x 35. I'm not gonna actually draw. These are also pages. So these are actually called leaf nodes. So these are called leaf nodes, and of course they're also pages. We only deal with pages, right? We don't have sort of other types of memory. Okay, so anyways, the main idea over this, why do we call it a B-link tree? If you look at it in a general thing, so these are actually pages, right? So you can again imagine this as being page 9. Again, pages are unique identifiers. Oh, they're never going to be the same twice. Anyways, but each of these pages will also have a pointer to its sort of next page, right? So now if you've done maybe a computer science class in your life, you can think, first of all, so what this project, or I guess what I've implemented is an index iterator over all of these, over essentially this linked list, right? Because you can sort of iterate over the entire linked list and sort of start spanning out different values all at once, right? So one more thing, what do these things actually store? Well, these things, so the way a B plus tree works, and then so a B link tree is just a B plus tree with like links, right? So the way this one works is these over here are called keys, right? So in Bastub we have just generic keys of 8, so these, or of 16 or whatever, and these can actually be compared with right, so you can think of these as generic keys, and generic keys can be compared with, I don't know, some sort of a comparator function or something like that. But these are just keys, and then the values that we store are these actual pointers. So they're pointers. So by pointers, we actually in this case mean just page IDs. Right, so I hope that this is clear. So this is for internal nodes, right? This is what internal nodes do. Right, so you remember that, right? You can remember this. Now, what do leaf nodes actually store? So leaf nodes, they store as keys, again, we have generic keys, but then as values, they store they store record ID. So what a record ID is, what a record ID is, it's essentially just a way to be able to find a tuple. And by tuple we mean like essentially a part, it's a row in a certain table. So a record ID is actually just a page ID and the slot number. So it's actually just a page ID slot number. And using a page ID slot number, you can actually uniquely identify a tuple, and a tuple is essentially a line in a row. So that particular tuple lives on that particular page ID, which you can ask the buffer pool manager for. And the slot number just sort of tells you, okay, which slot, so like a page ID can have multiple tuples on it, and then which slot of this particular page do I actually find the tuple that I'm looking for at. All right. So anyways, right, so this is what a b-link tree looks like. Now you can actually imagine how, for example, sort of a get value would work, or doing an iterator would work. So like for, I don't know, let's just, I don't know, imagine like some simple stuff at first. Let's just try to do get value of 38, right? So you look at the first one, you want to go to something that's bigger than or equal to 20, something bigger than or equal to 35, so you follow these pointers, and then you end up here, and you can, for example, binary search this over here, if it's like a, because the leaf nodes, like internal max size could be like very high, right? It could be like, I don't know, 4096. So binary searching it just reduces it to whatever that is, like 12 operations, I think. Or at most 12 operations, right? And so a get value would be very simple to implement. The only hard things to implement is inserts. So you have to be able to implement inserts and then also removes. So these are actually not easy. We're gonna start with removes. So removes actually have a single way of sort of, so the logic for removes looks like this. For inserts, we're gonna start with inserts, excuse me. So the logic for inserts works like this. You have to, so there's, first of all, there's simple inserts. So if you remember the, let's say somebody calls something like, and you can like reason about this from first principles, right? You can think, okay, somebody calls insert 47. It's clear you're gonna go like bigger than 20, bigger than 35. Okay, it's right here. Just try to drop in 47, right? That's very easy. It's like very simple. Or let's say if it were like 42, right? You'd say that's not as trivial. Well, it still is. You have to do is just delete that. Just drop 42 in there, put back your 44, and that's it. But the problem arises when you have, so in our case, remember, the leaf page max size is 3. So we're still okay here, right? So the current size of this is 3. So by the way, here the size is 2. And then the current size of this one is 3, which, so we've already hit the max size. Now, that is not a problem. But trying to do another insert, which is just insert 49, for example, right? If you try inserting 49 into it, you actually can't do that, because you would be exceeding the how would you call this? You would actually be exceeding the leaf page max size. Now the way you handle this is you do what's called a split. So a split, what it essentially does is, okay, first of all, think of all of the keys as if they were inserted in the same node, right? So you can think of them as, okay, let's say you had to instead do 43, so it's like right down the middle and it's not at the end, right? So you would like sort them and think of them like this. Now this again is your MT, mental MM. This is your mental model over here, right? So your mental model looks like an array like this, right? And you actually, what you do is you split this actual leaf. So by splitting the leaf, that means you create a new leaf. And then you move half of these. So you split this right down the middle. And you move half of these over here to another one, right? And now what you're doing is you are essentially you have what's called, you gain, essentially, you see, this is still valid, yet you feel the need for there to be someone pointing towards 43, right? So this 43 becomes your push-up key. Then your push-up, let's say that this new page that you created is P9, or to keep like the old syntax is p equals 9. So your push-up page ID, right? So we're gonna give those names. Your push-up page ID is 9 and your push-up key is 43. Now what does this mean? This means that now you have to resolve this conflict and go up here and actually insert 43 into the, so you have to insert 43 in the parent above you. Now how do you do that? Well, imagine, you see, in this case size is 2, and if you remember the internal max size, so the internal page max size is actually 3. So doing this is very easy. You just essentially do extend this, right? You modify its size and you insert 43 here, and this one points here, right? So really sort of not a big problem, right? Now you can sort of see the issue. Okay, what would have happened if, for example, now we wanted to insert, I don't know, something like 39, then 47, right? So let's try to go through this. Right, let's say another insert comes in, which is 39. So you go bigger than 20, bigger than 35, I guess, and then you do, so the size was 2 here and the size was 2 here as well, right? But now it becomes 3, right? So the size becomes 3 because what you actually end up doing is you insert 39 here and then 42 here. So these are what's called simple inserts, right? So this one is size 2. Let's say another insert comes in, which is 51. So you're gonna just, I mean, you're gonna go like down the 3 here, bigger than 43 anyways, and then you're gonna like insert here at 51, so size goes down, then you have size is 3. Anyways, now you can see that these are actually at a maximum at this point. Yeah, so whenever you split it, you should also update the like linked list to keep the linked list going. Right, there's probably some sort of way I should probably be explaining what latch grabbing is at this point as well. Right, I know there's like so many things, but we're gonna first do yeah, I'm not gonna be explaining that. So you can think of this as being single threaded at first. I guess it's actually not single threaded. There can be multiple threads, like sort of there can be multiple threads manipulating this at the same time, which is actually what happens in the code. Anyways, let's say you're gonna try inserting I don't know, something like 40 here, right? So your mental model now becomes, okay, you're gonna be trying to insert 40. That means you will exceed the size here. So your mental model is, okay, let's have all of these together. So this over here is gonna actually get split. So it will get split into 38, 39, and then you're gonna be doing this 40, 42, right? The size of this is gonna be 2. Let's say that the new page is 10, and then this one will point there. Anyways, then you can sort of scratch your mental model here, and your push-up key now becomes 40 because this guy doesn't have sort of anyone pointing to him. And then your push up key becomes 40 and your push up page ID becomes 10. So what do we mean by this? Push up key and push up page ID means, okay, we have to go to our parent and we have to actually point someone to 40. Now you can see, for example, here the size is 3. Our internal page max size is also 3, as it says here. So you can't actually sort of insert here directly. So what do? Well, you split it. So you split again, right? So again, think of the mental model. You do X. What do I need to insert in here? I need to insert the push-up key, which is 40. So you do X 35, 40, 43, right? So you're gonna keep X35 in here. You're gonna do 40, 43, right? But 40 over here is actually gonna have an X on it, and then you do 43, right? So this is your new page, which is, I don't know, page 11. So anyways, right, so you know now, and then you push up key, and then you push up page ID. So you know that 40 over here, essentially it has an X on it because this is the convention. The first guy in an internal page ID, it has an X on it. By that means there's actually not a key there, right? So we don't consider this a valid key over here. So you can think of there as actually not being any 40 there, and a 40 actually being there at the same time. I know it sounds confusing, but bear with me, okay? So the database system doesn't care about that 40, but the internal insert algorithm does. Okay, so this 43 over here is pointed to by that. And then because our push-up page ID is 10, the value, remember, the internal nodes have values as page IDs. So the push-up page ID now is going to be 10, right? So it's going to be pointing there. So we fix this. And of course, we actually split this right down the middle. So here we're left with just 43, 10, like that. And then the size is actually 2. And the size is 2 again. And now the push-up, so we have a new push-up key, which in this case is 40. Which is, in this case is 40. It doesn't have to be 40, right? But it's always sort of right after we split it. So right after we split it, it's the first guy here, right? And these guys over here, the 40 in this case, so the second half of like the imaginary mental model array goes in this internal node, in this new internal node that we just created. And then so it goes in the internal node that you just sort of created. So, and then this guy always becomes the push-up key. So the first guy in the second half always becomes the push-up key. Now remember, we have min sizes and max sizes for both internal nodes and leaf nodes, right? So, and those, so by the algorithm that I'm describing here, we're actually attaining multiple things. One of them is the fact that so the resulting key is actually going to be balanced. So by balanced we mean all leaves are at the same depth, and we're also going to attain the fact that we're going to be keeping our leaves, so all of our nodes within the limits of min size and max size at all times, right? So anyways, the push-up key becomes the first key in the second part of those elements, and then the push-up page ID is just the page ID that doesn't currently have a pointer to it, right? So again, scratch the mental model. We don't have a pointer to this guy. So what do? We go up again, and we can see here that we can just sort of, so the size here is 2, the max size is 3, so we can just add a new one, and our issue is then solved, right? Because this guy points here, and you can see that again this is a valid B plus tree. And look at this, now the 40 here exists, but the database management system acts as if it doesn't, because it doesn't matter, right? Here everything is bigger than or equal to 40, and then if you go to left here, you know, everything is less than 43. You can see every single one of the constraints is actually sort of validated, right? Think about that. So this always works. And you can sort of, again, if this one were full and it needed a split, so in this case it was sort of no, oh, I'm missing an L. In this case it was sort of like no split, right? But in case it actually needs a split, in case if that one also needed the split, you would actually split the root, right? So, but that's not a problem. You can split the root, right? Not a problem at all. Now, okay, so again, this is a valid B plus tree. Anyways, okay, let's do one more insert, because now I'm gonna explain what latch grabbing is. Okay, so hopefully you can reason from this about the fact that you can do any sort of inserts at this point. So like with the current logic, you can do any sort of different like insert, right? Like, whew. Right, so now I'm gonna try explaining what latch grabbing is. So the way we actually do is we have the concept of holding guards over these nodes, essentially, right? We can hold read page guards. So in database world, I guess locks are called latches, right? So the locks from operating systems, they call them latches. So they're actually it's just like sort of a mutex. It's like the mutex implementation from Linux, whatever that is. That's what we're holding, right? I don't know how mutex is implemented. I mean, I guess if I had to guess, there's like some atomic stuff with like atomic exchange, and you can like do it from those internals, but we don't care, right? We don't care. So a read page guard is sort of the promise that this current thread, so again, there can be any number of threads that access this at any point in time, right? So the promise of a read page guard is that this thread is only going to read the contents of the current thing, right? So you can imagine like get value, right? Just imagine what get value does in order to like wrap your hand around this. Right, a get value. So what a get value does is it essentially just does. Okay, let me grab. So let's say you're a get value on for 2, right? So what you're gonna end up doing is you're gonna grab a read page guard on page 7. So by read page guard, this means, so a page can have like any number of read page guards on it at the same time, right? So somebody can read like page 7, and there can be like 7 threads that read, or like 10 threads that read page 7 at the same time, but you can't have like somebody writing to it. So if somebody holds a write page guard, then nobody else holds any other type of guard. And then if somebody holds a read page guard, and then so there's like the only rules. Somebody holds a thread holds a write page guard, nobody else holds any type of guard. And then the other rule is you can have any number of read page guards holding a certain page. Okay, so the way getValue42 would probably do it is it would grab a read page guard on page 7, then okay, where does it need to go, right? It reads this, it says, okay, bigger than 40. Then it grabs a read page guard on page 11, right? Then it says, okay, well, we're smaller than 43, so I need to grab a read page guard and drop above, right? So I'm guessing it like does this, and then it drops the read page guard on 7, right? Because you don't need that, right? So you've like gone from here to here, you have a read page guard on this, and then you don't need this one. Then you need to grab a read page guard on page 10. Then you drop a read page guard on page 11, right? And then you have a read page guard. So you can see you sort of like dropped 7, you dropped 11, you just have a read page guard on page 10, and then you can actually read this and sort of like return to the user, okay, we have this, okay, here's like the value. So again, this has like an RID here, so just return like R2, for example. Right, so under the hood, again, this has like, so you just return R2, for example. Anyways, so why is this important? This is like sort of how getValue takes latches, right? Now, what we have is we have something which is called, I think, pessimistic latch grabbing. So for inserts, right? And the way this works is you're gonna actually start, so you're gonna grab write guards on every single node as you traverse downwards in your sort of, so you're assuming, by doing this, you're assuming that splits will happen, right? So there's like two things. One of them is splits don't happen, which case means you can, so the leaf where you have to insert has get size bigger than get min size, right? So it has like its size bigger than the minimum size, right? So if you were to assume this, you could just do an algorithm that sort of does read page guards as we did before with getValue. It does like different read page guards, and then as soon as it like reaches the last one there, it upgrades its read page guard to a write page guard and just writes to it. Okay, but what if, so that's easy, right? That's called optimistic inserts. Now what are pessimistic inserts? You think, so pessimistic inserts mean, so we assume splits happen. Pessimistic inserts. So we hold So this is pessimistic inserts. So what we do is, okay, imagine we're doing like insert, I don't know, 57. Like this is the perfect example. Now what we do is we actually do this. We grab So we're gonna do this. We're gonna say we grab a right page guard on 7, right? And then we say, okay, because I'm assuming, okay, this one may actually split, right? And notice that this is actually true, right, in this case, because if a push-up key comes up to this guy over here, its size, right, its size, no, this, so the leaf where you have to insert has get size less than get max size, my bad. So in this case over here, right, this guy has get size the same as get max size, which means that if everyone below me splits, then I'll have to split myself because I'll get a push-up key from below me and I'll have to split myself. So I grab the right page guard on 7, then I say, okay, 57 is bigger than 40, I have to go to 11, and therefore I grab a right page guard on 11. Alright, but notice here I notice something interesting. I notice that get size is actually less than get max size, which means this is what we call a safe node, right? A safe node means this condition over here is actually happens, right? So if this condition over here actually happens, then so if get size is less than get max size, then this is a safe node, which means if a push-up key comes down, so from below me, a push-up key comes upwards, then that actually means I can so a push-up key comes upwards, that means I can just insert it, and I know for a fact that I don't have to actually split it. So what I do is I can actually drop every single one of the right page guards on my path that I took so far, because I know I will never split and give a push-up key to someone above me, right? So this part of the tree I will never access, because I know that even if splits happen, it stops at myself. So I can actually delete everything. And imagine if here we had like multiple of them, right? I could delete all of them like that. So this is what we actually do, and we only keep the right page guard on 11, and then, okay, so 57. I have to go, so 57 is bigger than 43. I go down this path, and then I also pick one, so I pick a right page guard on 9. Now I see that I have to actually split 9. Again, remember the mental model. So what I'm doing here is I'll actually take, what was this? 51. Right, so I can do 51, 57. I know my push-up key becomes 51. Right, we can say that this is, for example, page 19 or something. So my push-up page ID becomes 19. Right? So I know that now this guy doesn't have anyone pointing to him, and I have to go upwards. I'm also grabbing a right page guard on the actual page that I'm creating. So, but this one is like sort of outside, right? So on 19, because I'm actually writing to 19. So I'm grabbing a right page guard on 19, I'm writing to it. And then as I go upwards, I know that I've just hit my safe guy over here. As I go upwards, I can actually start dropping these, right? Because I'm not interested in them anymore. I know I can just sort of like start going upwards, and then as soon as I hit the last one, I know this guy is a safe node, because this is what my algorithm has guaranteed me so far, right? So knowing that this is a safe node, now imagine that this is what one thread does, right? Now somebody tries to insert, I don't know, 9. This can happen in parallel because I'm not holding a right page guard on this node, right? I'm not holding a right page guard on 7 because I dropped it. So because I actually dropped node 7 and I'm not holding a right page guard on it, I'm only holding a right page guard on this guy and this guy and this guy, then that means that anyone can actually, someone can actually insert like 9 at the same time, and then the same mechanism will happen here, and then somebody could insert, I don't know, 25 at the same time, right? So this is how you can have like multiple threads actually inserting at the same time, because the way you're holding your right page guards is you're actually dropping them as you're iterating the tree, right? So then my push-up key is 51 and then it's 19, and then I can just drop in 51 here. I'm holding the right page guard as I do this, and then we're pointing it there, which is, so we're pointing it towards the push-up page ID. And that's mostly it for inserts. That's what latch grabbing is, right? So we have two sorts, pessimistic and optimistic, I guess. How long has this been? 51 minutes. So this is pessimistic inserts. This is what we call splits the leaf where you have to insert. Sorry, so assume splits don't happen. Only grab with page guards. Go to a leaf. Go to a leaf. Try upgrading to a right page guard and see then if assumption is true. Insert it easily. If assumption is false, do a pessimistic insert. So we assume splits happen. We take only right page guards, but we drop them. We drop all that we took on the current path when we see a safe node. Okay. Right, so this is how inserts work. Now, unfortunately, deletes are a little more complex. I mean, they're not that much more complex, right? They're not that much more complex, but they're still more complex. Anyways, this, I know. I mean, this whole thing is just like, your entire mind is just going, just imagine implementing this, right? I mean, explaining it just takes an hour and a half, I guess, if I also explain the links. Implementing it is just, oh my god, let me see. Anyway, so this is pessimistic latch grabbing and the other type of latch grabbing. Okay. Let's also present deletes. Right? We're gonna present deletes sort of in a more nicely fashioned way, in the sense that, okay, now we know how this works. So, again, you think that our max size is 3 and our min size over here is 1. So deletes, right? So first of all, let's imagine we are only handling leaf nodes. So if we're only handling leaf nodes, this means we have some sort of a parent, right? So the parent is right. Let's say we have something like tree 7. Or we have like, I don't know, something like 3. So there's 3 there, there's a 9 there, and there's like 9, 11, right? So you imagine leaf page max size is 3 and the min size is 1. So it's the same as here, right? The max size is 3, the min size is 1. Now if someone comes in and tries to delete, I mean, again, if you just have like something like delete 11, I mean, you just like come through the entire tree, you come here, and then you just like delete that, right? I mean, that's basic. That case is simple and easy to handle. But what if someone deletes 3? Well, if someone deletes 3, you actually have 2 mechanisms. So when leaf goes so you either do, you have 2 mechanisms. So you have 2 mechanisms which you can do, right? So the first one is, I guess, redistribute, steal from sibling, and the second one is, the first one is redistribute or steal from sibling, and the second one is coalesce. So redistribute means, okay, look to your left, look to your right, and then find someone where you can steal from. Now you can in case, so you can redistribute if your sibling, and by sibling we mean look at your parent, take your like current pointer here, look right, look left, these are your siblings, right? So this guy over here is your sibling and this guy over here is your sibling. Those are your only siblings. You can have at most 2 siblings and you always have 1 sibling. So you can, if your siblings get size is bigger than get min size, right? Like here 2 is bigger than 1. So the way you do this, okay, is you just steal it, right? So you just steal this guy, you like delete it from here, you place it here, and you update your parent, you delete this guy, and you place 11 here. Very simple. We're not gonna go over the case where you can steal from your left neighbor. It's very similar. So you can always you can also steal from your left neighbor, right? Again, very similar. Now let's say you deleted the 3, right? Because you first delete the 3 and then you steal it, right? And now the 3 looks precisely like this, right? So now the 3 looks like this. Now we have a problem. Let's say you delete 3 again, right? You delete 9 now. So delete 9 comes in, you go ahead, you delete it first. This is what you did in the case with 3. You first deleted. Now you look to your right neighbor, and let's say that this is like less than 3, so it's like something like 2, right? Now you look to your right neighbor, you see that you can't steal from him. You look to your left neighbor or sibling, neighbor, sibling, same thing. You can't steal from them. So what do? You coalesce, right? Or merge. So coalescing or merging means, okay, same mental model. Take all elements from here. Again, remember there may be more elements. We're just operating on the very, like, on this particular case when there's none. Okay, there's like no elements. But anyways, think of all of the elements and just place them like in one big sort of like place them in one big array in your head. Then take all of them, place them in the current, like you can always like think of your left sibling or like your left node and your right node, and you always take everyone from the right and you move it to the left, right? And then what you have to do is take the right's pointer in the parent, delete that, right? And then replace this by the first key that's in the left, right? I mean, replace the 3 here by the first key that's in your left, like that. So I hope this makes sense, right? Let's like take on a few more examples. We have examples around here. I don't think we do. Anyways, you probably got around to like handling I mean, I hope this makes sense, right? So you just sort of like merge them together. Like you think, okay, let's take an example where min size is 2 and then max size is 4. So this is okay, so imagine like min size is 2 and then max size is 4. So let's say you have something like 711, okay, 711 and then 1519, right? So again, these are leaves, right? We're doing leaf nodes, and then you have someone pointing at them this way. Right. So say someone comes in and he does delete 11. You realize that you can't actually like steal from, so you can't redistribute, you can't steal from any of your neighbors, so you have to coalesce. So okay, you first delete 11, you realize you can't steal from any of your neighbors, you have to coalesce, so you do 7, 15, 19, right? So everyone from right comes into left. This guy becomes your new sort of right, so this guy becomes your new, I guess, node. Now you don't actually have to modify the 7 over here, because even if you deleted the 7, right, the 7 wouldn't be here, and you'd instead have something like 11, 15, 19, but it isn't the problem. You do have to delete this 15 over here and the entire page, right? So if this were something like page 7, you delete the entire page and the pointer pointing to it, right? Okay, so I hope that's clear enough, right? So this is like the case for over here, right? You had to do a coalesce, right? So so these are deletes, only handling leaf nodes. Now let's look at deletes for internal nodes. So again, you have redistribute or borrow or steal, whatever, same thing, or you have coalesce, right? So they're essentially this, so you have like the same way of sort of fixing it. Right, so let's try to work through these examples. I mean, internal coalescing, internal nodes redistribution is a little harder, but it's still pretty close. So I guess this is a borrow left over here. And let me try to like think first what we're doing here. Right, okay, so why do we get into these cases first of all, right? Well, if you think about our thing from before over here, let's say here that like if we had for internal nodes a min size of 2, well, in this case it would still be valid, right? Because it's a max size of 3 and a min size of 2. But you see that we may actually end up like deleting another one due to some sort of coalesce before us, right? So we do a coalesce at the leaf level, and then that haunts us up. And what's happening is that the internal node size goes below the min size. So the internal node size goes below the min size, and let's say we're in this case here. So you see, let's say that the min size over here is actually 4. Right? So let's say that the min size over here is actually 4, and what happened is that we did some sort of like thing before us here that ended up with our internal node over here having a min size of having an actual size of 3. Right, so we can actually do a borrow left here. So what does a borrow look like? Well, a borrow looks like this. Okay, so we can actually, so we do the exact same thing, right? This is our parent over here, and then this is like the page. So we have a page ID that actually points to us. Remember, we have a page here, like, I don't know, 10, right? And say that this is P1 over here, right? Or just page 1, and then say this is page 2 over here, right? So the way we do this is, okay, first of all, try to think of what we want, right? We want to steal this guy over here, right? So we want to steal this guy, right? Just to add it here. Now, where would we add this? Right? We want to like steal this guy, but we can't actually do that. So what we do is what's called like a rotate, right? Like this. So what we do is we bring this key over here down into here, right? So you know this key over here currently points to 10. Now we bring this key down here and we make it point to P1, which is this guy over here, right? Then we bring this key over here up instead of it, right? So here is everything that's bigger than or equal to 1. and then everything that's bigger than or equal to 1 actually points to P2, right? And we point this guy over here to P2, right? And then here we just delete it, right? Here we just like lower the size of this because we're allowed to do this, right? So what we did is essentially we brought this key up, right? We brought the 1 up. We brought P2 down here, right? We brought 3 inside on a lower level, and we made it point to P1, right? Which was the page there. So you can see none of the invariants were broken, and we've actually borrowed a key, which is crazy. And I figured this out sort of by myself. I mean, Gemini said something, and I said, well, okay, you're probably right? And we actually made it happen. Anyways, borrow right, stop the video, try to reason through it. It's the exact same thing, right? It's the exact same thing. Okay, what does coalesce look like, right? So let's say here, so a coalesce of internal nodes. This is a coalesce. Probably figured this out by now, but anyways, imagine that the min size is 2 and that the current size of I guess the min size should be 3 if you want to like coalesce these, right? Because so again, the size of this is 2 and then the min size should be 3. Right? So if you look at this, these are internal nodes. Right? So the way you actually want to bring this, so yeah, so what you do is you just conceptually replace this with 9, right? So it's as if it's like the same thing as before, right? This x, but it also contains the 9. Then you take all of these and you place them on the exact same node, right? So you have like x, there should be a 7 here. I know what's wrong with this, right? There should be a 7. So the 7 points to, so you can see that the 9 points to like, I mean, this points to bigger than or equal to 9. This points to less than 15. So you can, conceptually, you bring in together. So again, mental model is x, 7, 9, 15 from before, right? So you just bring everything from right into left, and then you delete this key over here, right? So it's very similar. You just delete this key, which used to be the 9 here, and then you have x, 7, 9, 15, and then there's the 9, there's the 15, and there was like a 7, 8 leaf node here, right? And again, the way you do this is you do it with latch grabbing. So you have sort of the same protocol as you did before over here. So you do pessimistic latch grabbing where you assume, you don't assume splits. You like assume like coalesces, no coalesces, right? You assume either simple deletes or non-simple deletes, right? Because once you do one coalesce, then you should be assuming that it's a pessimistic latch grabbing protocol. Anyways, I hope we've ran through all of them. I'm just tired. I hope I've tried to explain this as well as I could. It was an interesting round though, very interesting round.